G'day chemistry students. In this video we are looking at dot points 7.3.1 and 2. This is a first video where we're going to be looking at chemical reactions. In particular, we're looking at addition and substitution of HX reactions with alkanes. Let's get into it. So when we're looking at organic reactions just in general, there's a little bit of a checklist that we can sort of run off. This is all the core information that you'll need to sort of understand an organic reaction inside out. These are all the tools that you need to then be able to go and apply your understanding of these reactions to a bunch of different problem-solving situations. The first thing that we need to know is the reaction type, the name of reaction. So for example, today we're looking at reactions of addition to alkenes and as well as substitution of HX to alkanes. That's the reaction type. We then need to understand the general equation. What are the reactants always going to be? What is the reaction always going to produce? If there's any catalysts, we need to identify what they are or what they might be, as well as any other reaction conditions. So that a lot of the time is whether or not energy sources are required. Do you need heat? What might the heat conditions be? Is there any atmospheric pressure changes? Do you need some sort of light or infrared or UV source? What we're also going to be looking at are the mechanisms and the intermediate products. Now, based on what we know so far about the HSC syllabus, what we've seen in exams so far, mechanisms aren't really a part of this course, but it's actually going to be a big focus of my introduction of each of the reactions. While you're not going to need to necessarily reproduce the mechanisms or understand them in complete detail, what the mechanisms help to do is help us to understand what the reactions are, why we start with our reactants, and why they end up being the products that they are. So when we're looking at our organic reactions videos, the main thing that I'm going to be doing is identifying the reaction type and showing you an example equation with the mechanisms that are in there, so we have a little bit of a better understanding of what the reactants and products usually are and how that sort of works. In our lessons, we're going to be doing some of those chemical reactions as well as looking at maybe some of the reaction conditions and summarizing all of the chemical reactions. So when I show you reaction mechanisms, there's a few different notes that may be a little bit foreign at the moment, so I just wanted to introduce them as well. If you see a dot next to an atom or a molecule, we can assume that this is a free radical. Essentially what this means is the substance has one extra electron, and that makes it highly reactive. That electron wants to form a covalent bond, and that's generally what those substances will do. We are also going to use reaction arrows. If the reaction arrow has half a head, it means that there's been a transfer of electrons, but only one electron has been transferred. If we see an arrow with a full head, it means, again, there's been electron transfer, but 2 electrons have been transferred. Generally speaking, when we see a reaction arrow, usually what we're seeing is the formation of a bond. Sometimes it means that there is a breaking of a bond and the formation of a free radical, and that'll usually happen when you see half heads. First reaction that I want to look at is the addition of X2 to alkenes, also known as halogenation. In other words, we're putting 2 halogens, which are marked as an X, so this could be fluorine, chlorine, bromine, iodine, adding them to an alkene, somewhere where there is a double bond. Going back a fair few videos when we were looking at bonding and structures of organic chemicals, I noted that there would always be one bond in a double bond that was a sigma bond, and a second bond that was a pi bond, and that the sigma bond was stronger than the pi bond. Because the pi bonds in double and triple bonds are quite weak, it actually makes them quite reactive, which is why we're going to see a variety of different addition reactions for alkenes in the next few slides. What happens with this alkene is the 2 electrons in the pi bond are able to go onto one of these bromines, and essentially the double bond that was between the 2 carbons becomes a bond between the carbons and the bromine. Now, because the bromine has picked up these extra electrons, the 2 electrons that were between the 2 bromines jumps onto the other one. What we end up with is the 2 carbons holding on to one of the bromines and a negative bromine ion, which now has an extra electron. That negative ion can then donate 2 electrons over to one of the carbons. And essentially what that means is that there'll be a bromine on either carbon. Another reaction that we might see is the addition of hydrogen to alkenes. Now, this reaction, and we can see this here, requires a metal catalyst. So what the metal catalyst will do first is separate these two hydrogen atoms. The double bond can't do it by itself like it did for the X2 reaction in this step. So these guys need to split first. The alkene can also attach to the surface as well. So essentially, one of the electrons will attach for either carbon onto the metal catalyst surface. What happens next is over here. Essentially, the bond between the carbon and the metal is able to move over towards where the hydrogen is and pick up the hydrogen and form a new bond. Same thing then happens to the other carbon and hydrogen which are attached to the metal as well. This then turns the alkene into an alkane. This process more generally is known as hydrogenation. Next reaction, we have the addition of HX to alkenes, which is hydrohalogenation. So rather than having just hydrogen or just Cl2 or F2 or Br2 or I2, we have a hydrogen halide. HCl, HF, HBr, HI could be any of those substances. What happens then is very similar to what we saw in the first example. The double bond is able to give its electrons over to the hydrogen in the hydrogen halide and form a bond between one of the carbons and the hydrogen. The additional bonds in the hydrogen halide then jump over onto the chlorine, and because it's got an extra electron, it becomes a negative ion. What we then see in our intermediate product is that one of the carbons picks up the hydrogen, that's this one here, and that there is then an empty spot for the chlorine to be able to add on. What we end up then with is, again, an alkane chain where the hydrogen and the halogen have been added on, one onto each carbon. Now, the interesting thing, which is different to the first two reactions that I showed you, is there are two potential products. If the first hydrogen adds onto the N carbon here, then the chlorine is going to go onto the middle carbon in the chain. However, if we went through that addition process again and picked up the hydrogen, but instead the hydrogen went onto the middle carbon, then the halogen has to add on to the end carbon, the first carbon that's there, meaning that we end up with two different isomers. We could either have, in this case, because this is a butane chain with 4 carbons, we could either have 1 chlorobutane or 2 chlorobutane. We're not going to go into detail about why there's a major and a minor product. We will end up actually producing more 2-chlorobutane than 1-chlorobutane. What I do want to acknowledge though, and in showing you this mechanism, is that there are going to be 2 products. And that is actually something that you need to remember when doing your general equations or applying your knowledge of reactions for addition of HX, that there will be 2 products, 2 isomers, which are present. And in this case, these will be position isomers. A very similar process of having 2 products happens when we add water to alkenes as well. When we add water to alkenes, we actually need an acid to be present. So you'll see at the start of both of these processes that we have a hydronium ion present. And this actually acts as a catalyst for this reaction. So in the addition reaction, what we see is that the alkene, the double bond, the pi bond that's there, will pick up a hydrogen just like it did in the previous reaction, meaning that one of the carbons will end up being saturated, meaning that there are 4 bonds, and the other carbon will be unsaturated. Essentially, there's another bond that it can form. This is where the water comes into play. The water will attach itself, but at the moment, the oxygen has 3 bonds, 1, 2, and 3. It's actually unstable at this point. The way that it restabilizes itself is to get rid of one of the hydrogens, essentially turning another water molecule back into hydronium. Now, end product that we have at the end is of the water, 1 hydrogen being added on one side and the hydroxide being added on the other. We can also see that the hydronium acts as a catalyst because we end up with hydronium at the end, and that hydronium is able to help this addition process again. Keeping in mind that this process would not happen with water by itself. Water does not interact with a double bond in the alkane and start that addition process. You do need this acid here to be able to saturate 1 carbon and leave 1 carbon unsaturated. This is where the water is able to add. Something that I want to acknowledge though is that again, we end up with these 2 products. In this first step, when we are picking up a hydrogen, there is a chance that the hydrogen can end up on the end carbon or the middle carbon. So in the mechanism on the left, when we do this first addition process, what we can see is that the hydrogen is added to the middle carbon, whereas in the mechanism on the right, the hydrogen is added to the end carbon. What that means is that when the water is added, it can be added onto two different spots, meaning that the hydroxide can end up being in the middle or on the end, in other words, primary or secondary. I've also got here a few different reactions that we saw previously that are addition of alkynes. So this is addition of X2, addition of H2, and addition of HX. Essentially, just what I want to acknowledge is that a very similar process happens. We just don't end up with an alkane at the end. We have an alkene. So one of the pi bonds is broken down, and whatever we are introducing, whether it's the X2, the H2, or the HX, then gets added on. One goes on to each carbon. Something to acknowledge, though, as well, is that with further reaction, we could do another addition process and add more X2, H2, or HX to then make different products as well. So the final reaction for this video is a substitution reaction. So instead of adding atoms onto a chain, in this one, what we'll be doing is substituting one atom for another. So for example, here we might have an alkane like this. So this is just methane, essentially. What we can end up doing is take one of these hydrogens off and replace it with a bromine instead. So instead of it being CH4, it would be CH3Br. Now the mechanism for this process is probably a little bit more complicated than some of the others. It's described in these steps here. We can discuss these mechanisms in class. What is most important to understand now is that a halogen can take the place of a hydrogen on a carbon chain given the right conditions. Thank you very much, everyone. In the next video, we are going to be looking at some chemical reactions which can be used to produce alcohols. But until then, have a good one.